My name is Caleb Luthai, and I will be talking about vulcanized rubber and other thermosetting elastomers. An elastomer is defined as a cross-linked amorphous polymer above its glass transition temperature. This is a lightly cross-linked polymer, not to the same degree of cross-linking as other thermosets, and it makes sense that it is above the glass transition temperature because anything below this and the polymer will have different properties, and these will be non-elastic properties. The different types of elastomers that I will be talking about are natural rubber, also known as polyisoprene, chloroprene rubber, ethylene propylene diene rubber, and silicone rubber. Elastomers go through a process of vulcanization, which is heating the rubber or other polymers with sulfur or other curatives to produce a polymer with superior properties, such as the one on the screen, which is natural rubber or polyisoprene, same chemical structure, and you can see the sulfur bonds are cross-linking the polymer chains. So here's a table of the properties of natural rubber, chloroprene rubber, ethylene propylene diene rubber, and silicone rubber, showing the glass transition temperature, specific heat capacity, elongation at break, ultimate tensile strength, and service temperature. I'm not going to read all of these off for you, but as you can see, all of them have a pretty low glass transition temperature, with silicone having a very low glass transition temperature. And the one thing that makes elastomers so unique from other polymers is the elongation. Natural rubber has a 600% elongation at break. This means it can stretch 6 times the original length before breaking. The other elastomers here do not have the same elongation, but they're still well above, like a polymer, like an injection grade polymer that you would use, much higher. The tensile strength of these elastomers is pretty low because, again, they're not designed to be a heavy load bearing polymer. They're they're used for their elongation, their elastic properties. And lastly, the surface temperature. They all have a decent range of temperature. Natural rubber, even though it has the highest elongation, it has the smallest temperature range that it can be used in. Silicone has a very wide temperature range that it can be used in, from negative 148 degrees Fahrenheit to 600 degrees Fahrenheit. This allows it to be used in very extreme conditions, both very cold and very hot conditions. This is natural rubber and polyisoprene. Both have the exact same structure and the repeat unit, which you can see on the screen. Very simple structure, and also, as I've listed, variety of different applications. Natural rubber is the most used elastomer as far as quantity, and a large amount of that goes into tires, but also used like footwear, lots of different automotive applications, and also like anti-vibration. So whenever you want to dissipate the vibration of a machine or something, you can use natural rubber. It does a very good job of this. Here is chloroprene rubber, and as you can see, the structure again is on the screen, the repeat unit. So chloroprene rubber is also commercially known as neoprene, which is a trademarked name. Um, it's a very good polymer for like chemical resistance and like weathering resistance, which makes it very good for some of the applications like gaskets and O-rings and like gasoline hoses. Very good because it is not affected by the chemicals and substances that will be around it. And also like wetsuits and orthopedic braces, like the different environments and stuff that this comes in contact to does not affect the chloroprene, which makes it ideal for these applications. Ethylene propylene diene rubber is a terpolymer of ethylene propylene diene. Very obvious. The structure here is again on the screen showing these different parts of the elastomer, but they all contribute different properties and make EPDM what it is. Applications listed again: gaskets, windshield wipers, like conveyor belts, used a lot for roofing sheets and like electrical insulation, but only for like the low and medium voltage. Silicone rubber is one of the most unique elastomers, very largely because of the structure. As any polymer, the siloxane group is the main backbone for the silicone rubber, and the three previous elastomers that I've talked about, natural rubber, ethylene propylene diene rubber, chloroprene rubber, all of those have a carbon backbone, and silicone rubber has a silicate and oxygen backbone. This makes it very different from the other elastomers. It's not affected by weathering and like heat as much as the carbon. Gives it a much different application fields. The large part of silicone that is used is the heat resistance. Like I talked about earlier, how it can go from like negative 148 degrees Fahrenheit up to 600 degrees Fahrenheit. That's why it is so widely used in applications like under the hood components in a vehicle, and it's also used for medical applications like prosthetics, but also molding for like other polymers, low temperature um, metals. Very good. You can cast the silicone on the outside of a part to create the mold, and then you take that part out and you can use it to mold that same part in the cavity. In conclusion, elastomers are very unique from other polymers that we use every day because of the elongation and the balance properties, making them perfect for like seals and flexible parts. And the variation of elastomer properties can be so wide because of the chemical structure that, that determines the properties of the elastomers. Changing that can change the properties. So many things that we can do with elastomers.